Hello, everybody. So today we're going to be doing ultrasound. Before we start, let's give all our credit to Mrs. Kathleen Goda for making these amazing slides. I'm going to be using her slides throughout the video. So let's give all the credit to her and her wealth of knowledge. Okay, fine. So let's start off with this useless sound waves. Okay. Sound waves are an example of longitudinal waves. We have learned two types of waves, transverse waves and longitudinal waves. Transverse waves, let me show you an example, can be electromagnetic waves. So we have over here like that. Okay, so you clearly saw my hand motion. It went up and then down, and then up and then down, and then up and then down. And that's how waves travel. But this wave is propagating this direction. But the movement of the wave is up and down and up and down and up and down. Basically, perpendicular motion of the waves. So when the waves are perpendicular to the direction of the propagation, they're called transverse waves. Okay, and we're going to explain how sound has both of the properties of transverse and longitudinal waves, but let's understand this. So this right here is a transverse wave. Now what happens in the case of sound waves is that we will have a medium. For example, let me just draw this real quick. Okay, this is a medium with all of its particles. Now when somebody screams, okay, let's say Mr. Tibor is screaming here. Okay, oh, amazing here as well. So he's screaming, yeah. So what happens to the sound particles is they bunch up and spread out in certain places. So it's gonna look something like, okay, let me just draw it now more clearly. They're gonna bunch up here, spread out here maybe. They're gonna bunch up here and spread out here. They're gonna bunch up here, bunch up here. I hope you can see the wave forming. Fucking breaking my iPad for you guys. Okay, yeah. So you can see over here how this area is compressed and this area is compressed, this area is compressed, but this area they spread out, or you can say rarefaction. Okay, so this is how sound propagates. It takes one of the particles and it makes the particle oscillate this side and this side. Now one thing to note is that this particle which has been here, it's not going to travel over here all the way here to propagate the sound. It's gonna stay here, and all it's gonna do is move back and forth and back and forth, back and forth, back and forth. It vibrates in its own place, and while vibrating it creates such patterns of compression and rarefaction. So you can see that the particles vibrate here and here and here and here and here, and the direction is also here. So their oscillation is in the direction of propagation. This results in them being longitudinal waves. Okay, now a very important thing to note is that only in gases and liquids we can see longitudinal waves. Okay, and now in gases and liquids only longitudinal waves are formed, where we can see the direction of oscillation and the direction of propagation to be the same. But in solids we might also get a bit of transverse waves. That's something to note. We will get, obviously, longitudinal waves are everywhere, but you can see over here how it says transverse waves are also can be formed. So it's possible, but not confirmed. Okay, it's not necessary that it has to be transfers in solids. So you can see over here in transfers, this is how sound moves. You can still see areas of compression, okay, and a refraction, but still the sound is the direction of propagation is upwards and downwards, and direction of oscillation. And this is a longitudinal wave. So that should be that. Okay, there is no net. Okay, just some important one. There's no net particle transport in the medium. As I told you, a particle which is here will not go all the way there to propagate your sound. Okay, it's going to stay there and vibrate back and forth and back and forth and back and forth and back and forth, and doing that is going to create the areas of compression, rarefaction. Then sound propagation requires the medium, of course. So we need particles to oscillate back and forth. So if there are no particles, what's going to oscillate? That's why in vacuum there is no sound. That's why in space there is no sound. It's cool, and this scream, even in space, if you scream, nobody's going to hear you because there's no propagation of materials or particles. In gases and liquids only we did this. Yeah, okay, fine. So let's start with the physical parameters of sound waves. So now we have two diagrams here where they have marked the areas of compression as the peaks of a wave and the areas of rarefaction as the valleys of the wave. Okay, this is not how sound propagates. We know it doesn't propagate like this. This is how it propagates. But they have mapped this into these waves so that it's easy for us to understand. Now, one thing to note, okay, clearly we can see that this wave has a lower frequency, lower f, and this over here has a higher f. This over here has a shorter wavelength, lambda, and this over here has a longer wavelength, lambda. Now, having such different waves still does not result in them having different velocities. These two waves travel with the same speed. Now, why is that? We can clearly see with our formula, which we have done before many times, C is equal to F lambda, right? So in these two mediums, what we can see is if we compare them, if the F increases here, we can see that the lambda decreases here. And if the F decreases here, the lambda increases here. You see where I'm going with this? So even if, let's label them now. Even if this is labeled 1 and 2. So C1 is going to be F1 by lambda 1 and C2 is equal to F2 by lambda 2. Now for the products to be the same, that means because we know the speeds are the same, right? That means F1 lambda 1 is equal to F2 lambda 2. Yes, because we can see where in C1 we know the frequency is low, but we know the lambda is high. Over here, we know the frequency is high, but the lambda is low. So they balance out each other somehow. They balance out each other and we get C1 is equal to C2. Okay, I hope that's easy to understand. I hope that's simple. Okay, now that was that. Now, we have this formula here, T is equal to 1 by F. Now, we should know that one wave is equal to a peak and a valley, or a crest and a trough. Okay, so the time it takes for one wave to propagate is equal to capital T. Okay, and that can be represented as 1 by the frequency. All right, now let's see if there's any important points over here. The particular medium wavelength and frequency are inversely proportional. Okay, so now another thing to note, these two, okay, they could be in the same, they are in the same object probably. Okay, now a thing to note is sound really depends on the medium. Sound propagation depends on medium. It heavily depends on the medium, okay? Because all of this propagation is dependent on the particles, how far away they're spaced, how much they're bunched up together. If they're more densely packed, like in a solid, then the sound's gonna travel faster, okay? But if they're more spaced out like gases, sound's gonna travel slower, all right? That's why when I hit a table, the person on the other side can hear pretty quick. But if I'm screaming, then the time takes a bit longer to travel through the air and to reach the other person's eye. Ear. Okay. So this formula, yes, is useful for this, but this may not always apply. This may not always apply because depends on the medium. Okay, but let's not complicate it more than what it is. And for now, just know that this formula is this formula, this formula is this formula. If they give you, solve the equation. Okay, pretty easy. Okay, let's move on. Over here, nothing too important. This is nothing too important. We don't have this. Over here, you can see they're just showing us how they map the areas of compression with increased pressure and rarefaction at decreased pressure, and they have created a wave for us to understand. Okay, moving on. Classification of frequency. Okay, there are some things that we need to know here. Of course, we should know what is acoustic sound. Acoustic sound is the sounds which we can hear. Okay, so very important note, because this may come as a relation something based question or a simple true or false. Okay, human hearing is from 20 hertz to 20 kilohertz. Please remember this, and there are some other values you need to remember as well. Now, like this one, medical imaging, we use typically 2 to 10 megahertz of ultrasound, and for therapeutic ultrasound we use lower frequency. That's enough, just lower frequencies like maybe there. Okay, now so remember these numbers. Now what do we have here? The frequency range of human hearing is between, like I said, the higher frequency sound waves are called ultrasounds. Okay, and while sounds having lower frequencies, then what lower frequencies than the acoustic range. This higher than this is ultrasound, lower than acoustic is infrasound. Is it worth noting that diagnostic sonography typically uses 2 to 10 megahertz frequency. Okay, very important to know, guys. So yeah, therapeutic application use lower frequencies but much larger ultrasound intensities are used. Now let's talk about speed of sound. I already talked about the propagation over here and over here, and I explained how this formula may not apply for all mediums. Yes, that is true. And that's why we have this formula, which does apply to all the mediums. What does it say? It says that the speed of propagation of sound is equal to 1 by the root of density and k. I don't know what this is called in Greek, but I'm going to call it k. And k is compressibility. Basically, how much can we compress this particle? How much can we compress this particle is the measure that is compressibility. Density, we know what density is. The more packed the molecules of a material are, the more density it has. Now, looking at this, people might think, okay, why is density down here? Because the more density, shouldn't the speed of sound travel more faster? But this suggests that the more density it has, the less speed it has, right? Because they're inversely proportional. Why is this formula kept like this? Now, important thing to note over here, these two are very closely related. Okay, they are, this can't be independent, this can't be independent. These two are dependent on each other. Okay, now let's say our density, we want it to be ideally low. Okay, but if our density is low, let's say like that, okay, our compressibility increases. Our compressibility increases a lot. We can press this a lot because of the space they have in between them. Okay, so now our compressibility goes to the roof while our density is low. This increase is so much bigger than this, okay, that ultimately results in the slower speed of sound. Okay, even though if we have low density. Okay, now when we have higher densities, okay, when we have a higher density, let's take that. Okay, higher density, compressibility goes underground. It goes to shit. You can't compress this because there's nothing to compress. All the spaces are filled. The spaces between the molecules are very less, so compressibility is very less. So what happens? The density being a little high, the compressibility goes all the way down. So what I'm trying to say is this, no, even if it increases a little or decreases a little, the response by K is magnitudes higher. Understand? So even if this increases a little, the relative falling down in value of K will make up for this being higher. I hope you are understanding what I'm trying to say. Okay? Over here you can see aluminum, a material with high density, highest out of all the others. High density. Okay? So we can see that the compressibility is shit, 0.009. Okay? So you can see the speed is the highest in aluminum. Now, if we were to take something that is less dense, like that, okay, like air, that's very less dense, but then you can see the compressibility goes to the roof. Okay, so that's why the speed ultimately decreases. Now let's take something like lungs. Has decent density, I guess. This is not even like respectable, bro. 0.40. But you can see how this, in relation to this is so much higher than this, right? So because of the compressibility being so high, the speed is low. If the compressibility is high, the speed becomes low. It's inversely proportional. So what I'm trying to say is the sacrifice of having a little bit higher density for a super low compressibility is worth it for getting more speed. So that's why don't be thinking that, oh my god, if the density is low, the speed is going to be high. No, the density is going to be high if the compressibility is high. No, sorry, density is going to be, if the speed is going to be high if the density is high. Okay, don't be confused. Shit. Okay, that was that. Very important thing to know. Oh god. Okay, very important thing to note here. The speed of sound in soft tissues is 1540 meters per second. This comes up again and again and again and again in the whole slide. So please remember this, guys. Okay? This we did. No, I want the laser. This we did. And compressibility is a measure of how easy it is to compress or deform the medium. Speed of sound in soft tissue. Please remember again, guys. Please remember. Boom. Moving on. Acoustic impedance. Okay, acoustic impedance is basically like resistance in a circuit. Resistance in a circuit is what? It's the inability to allow electricity to flow through the circuit. Okay? More that is, the more resistance it has, and the slower the speed of sound is. Now, acoustic impedance is something like that, resistance. Okay? So, it's basically the property of the medium to stop its particle from oscillating left and right or up and down. Okay? So if an acoustic impedance is high, that means this particle is not moving. It's not moving left and right, it's not moving up and down. If acoustic impedance is low, a particle is not free to move, but it has a lot of freedom to move up and down and side and right. Okay? So acoustic impedance is basically that. The resistance of a medium against bringing into motion its particles. And what is that represented by Z? Z is equal to speed of sound by the density. Okay? But if we can substitute the value of Z, which we know what it is, we get this. C is equal to, we know the speed of sound is this value. So when we substitute this into this, we get this beautiful formula, that is Z is equal to root of density by K. And please remember, this is the minimals. Important. I'm going to do the minimals later on, but yeah, this is important. And this as well, C is equal to Z by density, is important because it's in the minimals. Now, acoustic impedance is defined as the distance. We did this. Z is needed. Okay, a material constant. What do I mean by this? Z is different for every single material, and every material has a different Z, and it's constant in the medium. If this is a huge box, this whole box is gonna have one Z. This area can't have a different Z than this area unless they're made of different particles. Then if this is the same particles, then they all should have the same Z. Density of sound, energy passing through unit area perpendicular direction of energy of, okay, fine. Intensity, we need to know the definition first. The energy passing through the unit area perpendicular to the direction of sound propagation in unit time. Okay, so this is how we can measure sound. How can we measure sound? Basically, the energy. This is how sound intensity is measured. The amount of pressure felt by this membrane as sound passes through it. You can see over here the membrane pressure is high, that means the intensity is high. Over here the membrane pressure is low, so the intensity is low. Okay, so the formula of J, that is intensity of sound, is this: 1 by 2 and delta P square max, the change in pressure. Okay, initially it's zero, of course, it's going to be flat, but then no, how much of it bends, boom boom, like you've seen those speakers in the clubs or parties or something, they go boom 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 boom, they keep popping out because they're blasting loud ass music, that's why. Now this formula is in the minimals. Delta P max, what is the maximum change in pressure? That is nothing but the root of 2 acoustic impedance by the intensity of sound. Okay, over here we don't need to know this, we don't need to know this. Okay, now diagnostic imaging, we should know the intensity of sound in diagnostic imaging, the intensity of sound in therapeutic applications. There's nothing I can explain in this, guys, remember it, very important. Okay, now for US imaging sonography, intensity is applied which do not cause tissue damage. Okay, very important to know over here. Important to know is the therapeutic and the medical applications, because that's what matters to us and that's what's going to be asked to us. Okay, so we should know the ultrasound imaging sonography uses low ultrasound intensities so that we don't cause tissue damages. However, for therapeutic purposes, okay, tumor ablation, disintegration of kidney stones, okay, we use 7-fold higher intensities. Of course, if you want to destroy some kidney stones, you need high intensity sounds to shatter them. Okay, and these waves, I don't know why I drew them, but whatever. Okay, yeah, now absorption. Okay, now see this formula: absorption of sound. Of course, when we pass sound through medium, some of it is absorbed. Okay, some of it, because of the movement of the particles left and right, some of the sound is lost in other types of energies like heat, friction, whatever. Okay, now this formula comes everywhere. This is in X-rays, this is in nuclear radiation, this is everywhere. Because it's the same in the sense that J intensity is equal to the initial intensity Euler's number by mu and x. Now you should understand what some of these values are. J is intensity of sound after it has passed through the medium. J0 is initial intensity of the sound, which we can calculate using our respective formulas that we have. We just learned J is equal to, this is the formula for J. Okay, damn, that was. Now mu over here, mu refers to the absorption coefficient, which will be different for every single medium, and x is the thickness of the medium. Over here, this is x. Okay, now E, what is E? E is something called the Euler's number. Okay, now the Euler's number is something to do with calculus. Okay, I don't really know this, but it has you should have a number in your calculator or a button in your calculator which just says E. If you don't, then we can approximate the value of E as 1 second, as here 2.718. That should be the approximation for E. So whenever you're plugging in the values of the formula, you can write J, whatever the value of J you get, 0, and then 2.718 raised to minus mu by x. Okay, that should be fine. Now, what is this half value thickness? Okay, half value thickness refers to at what point did this J0 pass, at what thickness, after passing how much distance in this medium, did the J0 become exactly half. How much distance it traveled during that time is called x half. X half doesn't literally mean the half of x. This doesn't mean this. Okay? X half refers to the distance traveled after which the J0 became exactly half. That is, J0 means intensity became exactly half. That is half value thickness. Okay? Now, that is in the minimal, so that's why I told you to remember that. Propagation of sound brings particles into media into motion, causing friction between the vibrating particles. Oh my god, I'm sorry. And resulting in dissipation of a certain fraction. Yeah, this is easy. Okay, fine. Half value thickness, I told you what that is. Scattering. Now, while some sound is absorbed, some sound is also scattered. Okay? Some of the sound is absorbed in the medium, some of it's scattered all across. Now that is normal. Let me just erase this. Yeah, that is normal. Now, the mu, that is the absorption coefficient. Okay. Now this doesn't have really a formula as such, but this is basically just alteration of the direction of sound waves. If the sound waves is going this way, if it goes that way, this is called scattering of sound. Okay. Of course, this scattering ultimately results in the decrease in intensity for this wave. The direction was supposed to go all here. All of these sound waves going all the way here were also supposed to go along with this direction. But since some of them have gone this side and this side, the ultimate intensity of this wave decreases. Okay? This basically refers to the mu of a medium. The absorption coefficient of a medium is the sum of two things. It's the coefficient of absorption and the coefficient of scattering. Meaning that when you say that the mu of glass is this much or this much, whatever it is, it means that we're calculating how much does the sound passing through glass get absorbed first of all and get scattered, and then we find out the value of mu. Okay, that is that. Okay, over here reflection. Now sound waves over here kind of also act like, oh my god, let me just stretch. Sitting on my ass all day, you're gonna make my ass flat, bro. I don't know how I'm gonna do this for 5 years, but let's continue. Sound waves act like light rays when it comes to passing through two different mediums. Now, we know for light passing through, we use something called the Snell's law. So this is the medium, okay? And this is one medium 2 and this medium 1. If this has a higher n than this, if this n1 n2, if n2 is higher than n1, we know that the speed of light is going to be slower here, so that means you're going to bend lower, right? We know this one. In the same way, for sound waves we use acoustic impedances. Can this erase? Okay, so we use z1 and z2. Okay, now using these values we should understand if reflection is going to happen or refraction is going to happen. Okay, now at the boundary of a media with two different with two different impedances, acoustic impedances, what happens? Sound is traveling. Okay, let's say z2 is higher than z1. That means these particles are not going to move as much as these particles move. That means the speed of sound will not be as much in over here than is it here. Now, sound is coming here. Sound is coming. And now what happens is, since this some of the sound waves looking at, okay fine, z2 is higher. So some sound waves, they go back. Some sound waves go back. Some sound waves scatter. Some sound waves go through. Okay? Now using this information, these scattered, these absorbed, these reflected back, this is how we find out our ultrasound image, guys. Now, at the boundary of a media with different acoustic impedances, reflection happens. But guys, total reflection is a huge topic. Total reflection can't happen. Some of it will be absorbed. Now, when different speeds, okay, different speeds, by that I mean compressibility, density. Of course, we know the speed of sound is density, compressibility. So yeah, that basically means more compressibility, different compressibilities and different densities, but also different z. By why? Because come on now, z's value is what? Root of root of delta big K. So these two values have if they're different, then they have to be different in z and c. Okay, so usually even z is different. Reflection refraction basically just refers to the amount of difference between z2 and z1. If z2 is a fuck ton higher than z1, then yes, it will just reflect back. Okay, it won't even try to enter. Okay, but if it isn't that much, then some of it will go through, some of it will absorb back, some of it will jump back, some of it will scatter, you understand? But some of it will pass through. This formula no need to learn. Okay, now this is nothing much to learn over here. This is basically the concept that I explained to you. Not much to explain over here. Okay, over here it says acoustic impedance of the connecting medium is close to the acoustic impedance of the this guys. This is very simple theory based. Just after my lecture, please go through the lecture booklet so that it's easier for you to understand and retain the information. Now, look at this. Now we're gonna directly use the Snell's law for sound waves. Okay? Because see over here as it says, some of the waves they refract. Some of the waves they reflect. Some of the waves do pass through. Okay? Now using the Snell's law, we can determine how the refracted rays, speed, whatever. Okay? Now that's just how we're using Snell's law over here. That's nothing too big. Acoustic lenses. Now acoustic lenses. Now over here you could see this is a concave lens. Normally the rays passing should go out like that. But this isn't like light waves. But also this doesn't need to be shaped in a concave way. I don't know why it's shaped this way, but it doesn't need to be shaped this way as well. It could just be a square block like that, and still the sounds would diverge this way. Why? Because if the medium, if this has a higher z, z2 is higher than z1, then the sound traveling through will refract low anyway. It will refract like that anyway. Okay? So they will end up meeting anyway. So this doesn't need to be the concave shape that it does have. It could be any shape and the sound will still converge because it's sound and it doesn't really act like light waves. So over here you can see over here the phenomenon of refraction can be also utilized for focusing ultrasound. The so-called acoustic lenses are used for this. They are made from a solid materials wherein sound propagates at higher speed compared to the surrounding medium. Consequently, entering into the lens, okay, basically understand their acoustic impedance is different, which results in them bending and forming and focusing them, acting like acoustic lenses. Propagation of sound. Okay, formation of sound. Okay, so see now. Basically, to form sound, we need something to vibrate. And that thing vibrating will result in particles vibrating, and the particles vibrating will result in this propagation of sound. Okay. Now we need something now for the production of ultrasound. Ultrasound has super high frequency. Oh my god, I'm sleepy. Okay, now that means that to produce ultrasounds, we need something to vibrate super bloody fast. Now, what can we use to produce such high frequencies? Your mom's vibrator is not gonna cut it. What we need something which we can manipulate by adding electricity, by increasing or decreasing the voltage, which will create super high frequencies. And what do we get by that observation is we get our piezoelectric effect. Piezoelectric effect is something super cool. Now, let's look at this. Piezoelectric effect refers to certain particles which, on compressing, generate electricity. Super cool concept to think of, guys. Now, let me Boom. And I'll just copy paste this 1 second, guys. Okay, that should be enough. And oxygen right there. And I want it to be that shape, but I guess it has to be that shape. Of course, oxygen molecules are not in this shape, but bear with me, guys. S O S I O S I O S I. Now, if we were to isolate S I and O only, okay, we understand that O has a higher electronegativity, which results in the electrons being more in the orbits of O, which results in a partial negative and a partial positive charge over here. So instead of writing O and Si, what I'm going to do is I'm going to write them as minus and pluses, because that's what they have. They have charges like that. Now, if we were to find the middle point of all the negative charges, in a neutral atom without any compression, without any voltage, that would be somewhere here, where the distances are equal for all of them. Okay? And if I were to find the center point for all the positive charges, they would also be somewhere here. So the point at which, the center point at which the negatives and the positive have their centers is coincident. That means they cancel out. That means the net charge over here is 0. But when you compress them, like here, okay, the center where you find the equal distance for the positives is somewhere there, and the negatives is somewhere there. So now the negative is here, positive is here. That means they have a charge induced. Okay, and over here, as you can see, the negative charge might be somewhere here, because center of them is somewhere there, and the positive somewhere is here. Okay, so this has a positive, this has a negative. Understand, guys? So that's how charge is induced in these tiny molecules. And when you stack millions of molecules together like this, that's when you get the piezoelectric effect. Basically, applied stress results in a voltage, okay, which can generate electricity. Now, to generate ultrasound, we use something called inverse piezoelectric effect, wherein we add voltage to the piezoelectric material, and because of that, we get compression and relaxation of that particle. Okay, so if you were to, now after compressing, we get these voltages, right? Now imagine if I were to add a negative and positive voltage here, they would increase in size. But if I were to add a positive, if I was add negative and a positive here, they would repel and go inside. If I were to do this super fast, okay, with my current, then the particles will vibrate super fast, creating ultrasound. Okay, now for the detection of ultrasound, we use piezoelectric effect. For the generation of piezoelectric, for ultrasound, we use inverse piezoelectric effect. Now, detection. How come detection? Ultrasound waves are coming. Okay, our particle feels a bit of stress because of these ultrasound, and they compress. Because of the compression, we get voltages. Because of the voltages, we get electricity, and because of this electricity, we can identify ultrasound. I think that's pretty easy, guys. This. Alright, now we're gonna see the other two methods of generating ultrasounds. So guys, if the piezoelectric effect explanation was a bit too quick, I think it was, please try to go back and understand. But if you don't, you can always message me or whatever, if you know this. If you want, I will, oh shit, it's double M and then this. That's my Instagram. Want to ever ask me a question, whatever. Now, electrostriction is the process of generating ultrasound, and you use dielectric materials in them. What is a dielectric material? Dielectric materials do not conduct electricity. Okay, we have metals. Yeah, we have metals. They conduct electricity. We have wood, does not conduct electricity. Okay, but dielectric metals, it is the property of the material is influenced by an electric field, but it does not conduct electricity. It has some things inside it. It's called like, they have dipoles inside this material. Okay, dielectric materials have dipoles in them. Now usually the dipoles are spread out in weird formations all across the whole thing. Okay, but as soon as an electric field with a negative and a positive are applied, they all line themselves up. All the dipoles line themselves up according to the whatever. Okay, they line themselves up in a way that this plus minus plus minus plus minus plus minus plus minus plus minus, in a way which this is minus and this is plus, that way. So they influence the properties of the material. Electric field influences the properties of the dielectric material, but they do not, but this material does not conduct electricity. Okay, now, so what happens when you pass electricity through this? Because of the alignment of those dipoles within the material, there is a shape change. It's very small, but there is a shape shift. There is a shift in the shape of the material. Now, if you were to make this side positive and then switch them quickly and make this side positive and this side negative, and then switch it again to make this side negative and this side positive, what happens with those dipoles? They go up. They go up and back and forth, back and forth. They keep spinning. That results in the material changing shape again and again and again and again. Okay, which results in, you guessed it, ultrasound. Super fast vibration results in ultrasound. Okay, now elastic deformation of a dielectric material in electric field. Arrangement of the electric dipole increases the thickness and direction of the applied electric field and reduces the thickness perpendicular to it. So as you can see over here, the dipole, as I was talking about, when you align them like this, you can see that the total distance, this is the material, suppose. Now when you align the materials that way, this is the material. See how it has increased in length? So that's how I'm saying that the shape changes. Okay, so one thing, very important thing to note, it's a non-reversible reaction. Like piezoelectric effect, we can produce, we can pass electricity through it to make it vibrate and then to produce ultrasound. Okay, but then we can also pass ultrasound through a piezoelectric material, and then because of the shift happens due to the pressure of the sound waves, produce electricity to calculate in a machine what the ultrasound is trying to tell us, right? So we can detect ultrasound using piezoelectric effect as well. But using electrostriction, we can only produce, not detect. Okay, non-reversible mechanical difference does not induce electric field. Magnetostriction. Now magnetostriction is done by ferromagnetic materials. What are ferromagnetic materials? Ferromagnetic materials are materials when you pass electricity through them. This is a ferromagnetic material. You pass electricity through it for some time, and then after some time, when you remove this, the circuit, this material now becomes magnetized. Okay, so that's a ferromagnetic material. It has a tendency to get magnetized really quick due to electric field. Okay, now when you do this, when you pass a magnetic field through a ferromagnetic material, the change in dimension occurs. A change in dimension occurs in magnetic fields. Okay, now if you were to switch the dipoles of the magnet around the material and be like, now it's south and north, now it's north and south, now it's south and north, now it's and now, okay, understand what I'm trying to say? The material shape changes a little bit like that, then becomes small, then becomes big, then becomes small, etc. And then what ends up happening is there is a lot of vibration, which results in, you guessed it, ultrasound. Okay, Now, the cool thing about this is it can be reversed. Inverse magnetic restriction, mechanical deformation changes the magnetic properties. Okay, so that means that you can affect the magnetic field, or you can produce magnetic field due to the pressure formed by the mechanical deformation. So you can produce, yes, and detect, yes. But usually we don't use this. We usually use piezoelectric materials. Okay, piezoelectric materials are really common. The watch I wear on a daily basis is run based on the piezoelectric property. It has a small quartz crystal inside it, which when I wind the, oh, this is a watch and it has one of those wheels on the end, right? Those wheels in a mechanical watch, you need to wind them every day. So you need to turn them a certain number of times every single day to wind them. And what the winding does is it produces pressure on that quartz crystal. And then because of the pressure, there is electricity produced, and that's why the watch runs forever. It's not the same way for cell watches, in which you put a battery inside and it stops after some time. But all these famous brands like Rolex, Audemars Piguet, Richard Mille, all these watches, they run on the principle of quartz crystals, and that's why they run forever and ever, because you can just wind them and electricity will be produced. This is why Rolexes and all, they are a generational watch. They get passed down because it can never, because of the piezoelectric crystal, they work forever. Boom, whatever. Please go through this. It has two names over here. Magnetic restriction is Joule and also Villary effect, but this is the reciprocal effect. That is when you detect ultrasounds, okay, that's called the Villary effect. But when you are producing ultrasound, it's called the Joule effect. Remember that, please. Diagnostic sonography. Okay, so now we're just talking about, what kind of material, what kind of waves, or what are the techniques with which we produce ultrasound. Now, using piezoelectric transducers, what is this transducers? Transducers are those machines that you see, a doctor use on a pregnant woman. Okay, this is the transducer machine. This is the machine which produces the ultrasound, basically. Okay. Now, there are two ways you can do this. You can use the pulse technique and the continuous technique. Now, the continuous techniques is not used in medical procedures. Mostly it's not. But there is one place where continuous techniques are used, and this is a very weird way that I'm going to say it, okay? Now, have you ever seen gold being cleaned? Gold or rust coming out of iron. There's a special way that professional cleaners use ultrasound to clean this. So, they put a transducer with super high frequency ultrasound underwater. Okay? Underwater. And when they start the ultrasound, the water starts to vibrate like crazy. And then when you dip an iron rod with rust on it, you dip this inside the water and you remove it, it's crystal clear, like a new block of iron again. All the rust gets shattered, because of the ultrasound waves. So that's one way you can use continuous wave, where you're just blasting ultrasound all throughout. There's no pause, nothing. But then now we're going to learn about pulse methods later on. Interaction of the ultrasound with the human tissues. The good, the bad, ugly, whatever. I'm going to do that. Detection of the echoes. This we will do. Okay, now let's look at this. An ultrasound pulse is emitted into the body and subsequently reflected echoes. Okay, this is the pulse echo method. In ultrasonography, which is usually the ones that we use in medical scenarios, that's showing the baby on the screen, or showing your kidney stones or something like that. We use something called the pulse echo methods, and there are a few pulse echo methods which we will learn. Okay, now I need a diagram of the pulse echo right here. As you can know, not even this right here. This is a pulse echo method. These are pulse echo methods. So you pass a small pulse of ultrasound, which is usually 2 or 3 cycles. See, this is one cycle, then this is another cycle, this is another cycle. A pulse of ultrasound, and then you wait for some time. This is called the pause time. Why do you wait? Because when you're passing ultrasound, you suppose this is your leg. Okay, this is your knee, this is your calf, and you have your bone over here. Now, when you're passing ultrasound through this, you pass the ultrasound and then you wait for some time for the ultrasound to bounce back, because there's going to be a bit of reflection. bounce back into the transducer to detect that and tell, okay, fine, bro, on the screen it shows, bro, there's a bone there. Understand what I'm trying to say? So you need time to detect the echoes coming back, or the reflections coming back from the ultrasound reacting with the tissues in our body, right? So that's why we have a bit of pause time. Now there are some properties where we need to listen and look at. And sorry. An ultrasound pulse is emitted into the body, and subsequently the reflected echoes are detected to gain information about the position and sometimes also the structures of the echoing surfaces. Of course. Now in pulse echo methods, very important thing is the same transducer is used for generating ultrasound and detecting echoes. So this is called a transducer. This guy will produce an using piezoelectric materials. It will produce an ultrasound with 2-3 waves, okay, and then it will also detect the ultrasounds coming later on, okay. And then what else do we have? Yeah, reflection. Okay, how are we forming this image? Let's say we pass ultrasound through this object. Some of it, as I said, passes through, some of it reflects back, some of it gets scattered. Okay. Now, using this information and this information, how much has been absorbed, we form an image on the screen showing that, oh my god, bro, you have a baby in your stomach, or your, yeah. So that's basically it. The point of image formation are reflection and soft tissue scattering. Absorption decreases the intensity of the echo signals, while scattering may also contribute to artifacts related to the false positioning of certain tissue interfaces. What does this mean? Because of scattering, now ideally what you would want like a bone, suppose your ultrasound goes there, reflects, some of it reflects back, some of it, that's no problem. Absorption is no problem. Reflects back and you're like, okay, fine, we see a clear image that, okay, there's something over here. But then because of scattering, what happens? Sometimes there's scattering all across, okay? You get this blurry image and you're like, you can't determine the position of whatever you're trying to look at. So it's not anatomically accurate. That's what you say. Now, using this ultrasound, what we can find out is, now we know the pause time, okay? We know the time it takes for the ultrasound to reflect back to the transducer, okay? So we know the time it takes back. We know the speed of sound in soft tissues is 1540 meter per second. So using the speed is equal to distance by time formula. So we know speed, distance, and we know the speed, and we know the time. So using that formula, speed and time, we can find out the distance of the materials from the transducer. So we can say, oh, this bone is like 3 centimeters deep, or something like that, okay, something like that. So that using since the speed of propagation of sound is known, we can provide information of the distances of the echo surfaces from the transducer, okay. Now, upon image formation, now what happens? There's a thing called amplification, okay. It's called time gain compensation. What happens? Now, when we pass a ultrasound through a body, this is the body, okay? This is the body boundary, and the ultrasound is passing through. Now it hits a bone here, and it's coming all the way back. Now, while coming back, it's gonna lose energy in the form of heat, like obviously because of the friction of the movement of the particles. So when it comes back here, the reflected intensity is not actually what was sent through. So to compensate for the later the ultrasound comes back to the transducer, the more it is amplified a little bit, because we know the more time it takes to come back, the more it has lost its energy, or its intensity. So what the transducer does is, it just amplifies that last ray coming late a little bit more to get a more accurate image. Understand what I'm trying to say? So it's just like, I'm thinking of an analogy right now. It's like, okay, screw it, I can't think of an analogy, okay? So basically, you know that the incoming ultrasound wave has a higher amplitude or a higher intensity, but it has lost that intensity because of passing through so much soft tissue. So the transducer is like, okay, let me amplify it a little bit to get a more accurate image. Boom. Ultrasound generation, like I said, pulse mode. This is the transducer. Now, important part is we need to learn about the major components of a transducer. Okay, so let's learn. So let's look over here. First, we have our piezoelectric material. Of course, we need to have a piezoelectric material, okay, which is thickness of the which produces the ultrasound and also detects the ultrasound. Now, important, thickness of the piezoelectric material should be half of the ultrasound wavelength. So we take a wave. Let me draw a line. Take a wave. This is the wavelength. Okay, this right here, that's the wavelength. To another crest, that's the wavelength. So the piezoelectric material should be half the thickness of that. Understand? This is something it just has to be like that. Okay, don't ask me why. Backing block. Okay, what is this? This is the backing block. This has a very high absorption coefficient. Okay, why do we need it to have a high absorption coefficient? Why does this need to have a high absorption coefficient? Why? Because it acts like a dampening unit. Okay, so we know that we're sending pulses of ultrasound. Okay, pulses, boom, 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 boom. Okay, what we needed to do is to stop immediately after sending 2 to 3 cycles, right? But that's not really very easy because we're stopping such a high frequency of sound, because ultrasound has so much energy in it. So to stop it, we have this very absorbent material so that it damps the rays, and then it becomes and then after 2 to 3 cycles it completely stops. It's like adding pillows to your floor so that when you jump on it doesn't hurt. Okay, so why does it not hurt? Because it absorbs all of your energy which is falling onto the ground, and it dampens it, so your fall doesn't hurt. I hope you understand what I'm trying to say. Okay, and then there's the couplant layer. This is the couplant layer, the layer just that makes contact with your skin. Now the thing about this is the attenuation. Oh no, whoa. Is anything weird going on there? No, it wasn't. Okay. Now, the acoustic impedance of this couplant layer should be similar to your skin, the soft tissue or your skin. Why? Because we know if the Z1s and Z2s are way different from each other, they reflect back. So if they're the same, they pass through without any problem. Okay? And that's how we want. That's why the acoustic impedance of this couplet layer is very important. See over here. Couplant layer should be the root of the source and the skin. Source, you guys know what I mean. Source. So, in ideal acoustic impedances, the couplant layer is also equal to geometric mean of the acoustic. This is whatever, guys. You learn the formula. This is the formula, but we don't need it because it's not there in the minimals. Okay, now this is another method. Now we're gonna see the pulse methods. What are the methods that we're gonna see? We're gonna see them now. So this is one of them, which is send a pulse, wait for the echo to come back, and then form an image based on that. Okay. Now see, this is the thing. Pulse is called pulse repetition time. Okay, and echo signals are detected in an interval. This interval called pause time is more famously called PRT, pulse repetition time. I try to sound very fancy for you guys. In reality, I don't really speak like this, but I want to sound fancy for the video. Yeah, pulse repetition time, PRT, or pause time as it says, but this is cooler, PRT. Okay. The length of the PRT can be changed between 100 microseconds and 100 milliseconds. Longer PRT ensures longer period of time for detecting the echo signals. Thus, echoes arriving back from tissues deeper inside the body can also be detected. They have a short time and they just like boom, boom, boom. Where are you going to detect the rays, brother? Where are you going to detect the ultrasound, brother? So you need enough time to detect the ultrasound. Okay, even coming back from deeper parts of the body. Now, this is another method. This is called an one-dimensional A image. what is an A image? An A image basically just plots the intensities of the amplitude of the graph coming. Okay, so see, basically, there's going to be a graph. There's going to be a graph. Let me draw the graph. Okay. Over here, you're going to have the amplitude. Alright. And amplitude, and over here you're going to have the time of arrival. Now, what are you going to do? The rays are going to go something like this. Now, you're going to send an ultrasound in your body, and you're going to wait for the ultrasound to reflect back. Okay. Now, the ultrasound which reflects first is going to be like, okay, fine, that's the intensity of the ultrasound. So that means this part is closer to the body, whatever this part may be. Since it has reflected faster, that means it's closer to the body, and because the time is less. Then later there's going to be another ray, something like that. Oh my god. Then some other ray like that. The rays going like this, since this is taking a longer time to come back, that means it is farther inside the body than this ray. Okay, so this is the one-dimensional image. This is all the information you get. You get the information of the distances of the objects from the transducer. Okay, so look at that. Using our formula, s is equal to speed is equal to distance by time. We can find out the distance using speed by time, because speed we know is 1540 meters per second, and time we can plot it. We can understand what this is. And basically over here, instead of using speed, they use speed of sound in any medium. Ct is equal to 2d. Now why 2d? Why divided by 2? Because we're calculating the time of us sending the ultrasound and us receiving the ultrasound. This whole cycle is 1. So basically we have to divide it by 2 to get only this side. Only this side will be divided by 2. I hope you understand what I'm trying to say. So that's a one-dimensional image. Okay, that's an A-type image. Now let's look at a B-type images. Now the B-type images, echo intensity represent the brightness of the dot. Okay, now basically it's the same as an A-type image. Okay, so we use an A mode image like this. Okay, where we detect the signals coming later on, and this is okay. And using the intensity of that, now we see, okay, fine, this has a higher intensity. This is going to be a brighter white. This has a lower intensity, it's going to be a little gray. This is a very low intensity, it's going to be that. If it was flat, it would be black. You understanding? So based on the intensities, looking at the A image, we're gonna plot those intensities to the respective brightness of a pixel. Okay, so we're gonna take a pixel and then we're gonna map it to the intensity of the A mode image. If it has a higher intensity, we're gonna make the pixel brighter. If it has a lower intensity, we're gonna make the pixel darker. Okay, and using that we get A image looking something like this. This is an A-type image converted into a B-type image, and where we can map it out using the pixels basically. Okay, so what does this show us? See, what did we get in an A-type image? We get a graph like this, right? In an A-type image, we flip this around and we put it like this, because we know that the rays coming first represent the material which is up top, and the rays coming later on are something below. Now using this, we map the intensities of the pixels, and then we get an image something like this. Okay, so I hope you understand how we get a B-type image like that. Okay, M mode images are very important diagnostics of heart. Okay, so yeah, usually M mode images are nothing but, cancel this. So these rays are mapped to their subsequent waves. Okay, and then we get something like that. Okay, so M mode images are basically B mode images. Okay, brightness images in a one-dimensional B mode images created by subsequent ultrasound pulses put next to each other, function of time. Using this method, we can visualize the movement of okay. Now a B mode image. Now this is an A mode image. A B mode image would look something like this. But these 5 pixels are not enough to form an image. So what do? This is the transducer. So we take the transducer over here, and we get its A mode image. Then we move the transducer here, and we get the A mode image for here. and the brightness image for here. Then we form all these pixels. We go all the way across the body and we form all these pixel like here also, here. And when we do that, we get this whole image. So we take our transducer, we run it to the body all the way across here and here. We get each lines. This let me take this as each line over here, okay? Each line has its own A image, to which we have mapped the B images to get the brightness of the pixels. And then we have joined all these lines together to get this M mode image. Okay? I hope you guys understand that. Now, we have 2D B images. B images, again, like I said, B image is the B image, which is mapping the A image to their subsequent pixels. And depending on the intensity of the A image, we get the intensity of the pixels in the B image. Now, we can use two methods to scan. We can use linear scanning, going straight like that, and sector scanning. Now, linear scanning, you can see just how we can get an image like this using linear scanning. And now you may think, how do we get this guy? 3D images. Okay? How? If we take our fat stomach like here, we're looking from top. Okay, this is a fat ass stomach. And we take a transducer and we're passing it all the way throughout the trunk. Now, using the linear images of all these areas, okay, using all this information, we can produce a 3D image which looks like this. Okay, that looks so creepy, bro. If I see this in my wife's stomach, bro, I'm punching the screen. Okay, whatever. So these 2D images are formed as a sum of many one-dimensional B images. Okay, that I basically told you. Like, let's divide this into lines, like I told. Okay, each line has its own A mode image, to which we have mapped the pixels, and then joining all of these pixels together, we get a B mode image. So as I said over here, the 2D image is formed as a sum of many one-dimensional B mode images. Now, linear scanning, sector scanning, this is basically, you understand what this sector is spreading out like a fan, linear is straight up. Using many 2D images, we can form a 3D image. And imaging artifacts, okay, basically over here, what they're trying to say. Okay, this you see over here. This is not an object, like this is the object, but this is not an object. This is the image of this. How do we get this? Why? Because the diaphragm has a high reflection coefficient. Okay? Okay? So what happens is this is a real object which is not supposed to be in our body, for example. Okay? So this completely reflects all the light, all the ultrasound, sorry. And then because of it reflecting, this guy, what happens is it absorbs some, of course, diaphragm absorbs some, and diaphragm reflects some as well again. So it reflects light on this again, and this guy reflects that light back to the transducer. So again, this is the transducer. It sends it ultrasound waves. Now it hits this object, comes back. Now, but then some of it is reflected here also, and then this diaphragm reflects some of that rays again back to this, and then there's more coming back. So because of that, there are two images formed basically because of like they act like mirror images of each other because of the diaphragm. Diaphragm is this guy who reflects the reactions back and then sends them back. So the transducer is like, oh, maybe there's another object here. But what's happening actually is this object is just scattering the ultrasound back here, and this guy is scattering it back there to the transducer. And then this guy, and then the transducer ends up thinking there's two things. But this won't be asked. I don't expect it to be asked, so don't need to worry about this. Diagnostic sonography resolution. Okay, resolution, guys, in microscopy we learned what resolution is. So it's basically the distance at which we can distinguish 2 points. So now there are 2 types. See, this axial is referring to, like, this is the transducer, for suppose this is the transducer. This is the transducer, okay? Now, these are 2 points. Now, what is the distance, the minimal distance at which I can say confidently that these 2 points are separate? Okay, that is what we're trying to find with resolution. Now, there may come a point where they're so close to each other that this ultrasound machine is like, oh, this is just 1 point. I don't understand them as two different points. So I just think this is one point. So what is that distance? That distance is where, that is the limit of our axial resolution. Axial resolution is basically this: distinguishing them based on the same, they're not on the same level, but they're in the same line. Okay, in that way, they're in the same axis. But then we have lateral resolution, which is this same thing, but they're on the same level. So what is this distance? The minimal distance at which they can be distinguished as 2 points. So that is that. Okay. So please read over the booklet. I mean, this is all you need to know. I'm pretty sure this is all you need to know for the resolution thing. It's not a very important topic. Now we have Doppler effect. This formula, forget this. But let's understand what Doppler effect is. A moving object. If you have seen a duck in a pond or something like that, the duck's going to be here. Okay, this is the duckity duck. Okay, it's going to have its beak, whatever. Okay, when it's automatically stands there, it has ripples all around water. But when it starts moving in the water, you can see this is the duck, suppose. Okay, when it starts moving, it makes waves something like this, where this side, where towards the direction that it's moving, the waves are highly bunched up, increasing in a higher frequency, but the waves behind it are getting spread out farther and farther apart. If you have seen this, that is Doppler effect basically. Okay, so the object moving this side, okay, the car's moving there. Okay, you can see that the waves in the direction of the movement are bunched up together, but behind it is farther away. So basically the frequency of this guy, let's say a guy is staying here. Okay, a guy is here and a guy is here. Looking at this guy's perspective, the car is coming towards him. So the frequency of the sound that he hears is more. Okay, but then when you come back here, okay, now suppose the car is moving this side. So the frequency of the sound over here will be higher for this guy, so his frequency will be higher. Understand? So this is Doppler's effect. Okay, now so I hope you guys understand what Doppler's effect is now. So basically the direction of movement, only the frequency increases. Guys, I've seen many past paper questions where they ask like, in Doppler effect, the observer's intensity is higher than the person who's away. Intensity is the wrong answer. Only and only mark that stuff correct if it's mentioning the frequency, guys. Only the observer's frequency increases. Now let me explain this in another way. This guy in the car, when he's horning, okay, let's say this guy was standing in the middle of the road like a moron. Okay, so this guy is going to be horning all the way from here till here. For him in the car, there's not going to be any change in the volume of the horn. For him, it's going to be beep beep all the way across. But for this guy, when the car's here, he's going to hear a faint noise of the thing. And then when the car comes closer and closer, he's going to hear the honk getting louder and louder. And then after that, when the car passes by, he's going to hear it get slower and slower. The same in how if you've seen F1 or any race, when the car comes past, it goes zoom. You see how that it comes close and then the volume increases, and then when it goes far it decreases. You see that? That's the worst impression ever, but I hope you guys understand. That is that. So that is Doppler's effect. Okay, Doppler's phenomenon is often expressed and used. It's the source of observer and relative motion to each other. The frequency differs from the emitted one. This phenomenon can be used both in medical and electromagnetic waves. Okay, guys, so that's that. You need to learn about that. And these later on, all of this is theory. So I'm gonna leave it from here on, okay? Because I don't want to waste your time, because all I'm going to do right now is just read off these slides, because there's not a lot to explain in this. Okay, so I'm going to leave it over here. I hope this was an informative video. I hope this helped you. This is kind of like just a quick revision. Please, after this, go through the lecture booklet, okay? And don't completely rely on this video. This video is not enough to get you to pass or something, okay? But now what we're gonna do, we're gonna look at the minimals right here. Give the frequency of the sound waves audible by a normal human ear. This we have done. Okay, we have done this 20 hertz to 20 kilohertz. Okay, what is ultrasound? Ultrasound the frequencies between 2020 kilohertz and 10 raised to 10 hertz. Basically, guys, this is simple stuff. Get the definition in unit of sound intensity. We had learned that the energy carried by a sound wave perpendicularly across unit cross-sectional area per time. Okay, we had learned this in intensity. Where did it go? Right here. Energy passing through a unit area perpendicular direction of sound of propagation. Okay, so I hope that wasn't too hard. And then what else do we have? Yeah, define the words compressibility of the compressibility, bro. Come on, how much you can press a material? Boom. Okay, compress a medium. Define acoustic impedance of a medium. Acoustic impedance of a material is can be resistance of a medium against bringing its particle into motion. Okay, basically how in a electrical circuit resistance is, over here for a sound wave, acoustic impedance is the same thing as resistance. Okay, this is the formula. Write the formula and express what the values are. Okay, describe the relationship between this is nothing. This is asking you to define a relationship. Suitable for generation of ultrasound, inverse piezoelectric effect. Remember, guys, not piezoelectric, inverse piezoelectric. Electrorestriction and magnetorestriction. Remember, electrorestriction cannot detect ultrasound, but magnetorestriction and piezoelectric effect can. Okay, describe the relationship between amplitude. This is again a formula. Please remember, I can't explain what a formula is. What is cavitation? Attractive forces between fluid particles may be overcome by the alternating pressure changes. Oh, this is the last theory portion that you had to learn. Okay, so yeah, that was the last theory portion you had to learn. This is a simple question answer. I hope you guys can do this by yourself. How does intensity of an ultrasound change while it passes through a certain medium? This we learned. This is the formula. Okay, this basically they're just asking for the formula. You give the formula and you tell what all this stuff is. This is the intensity after passing through medium. This is the initial intensity. This is the absorption coefficient. This is the thickness of the medium. Okay, what is reflexivity? The extent of reflection is determined by the acoustic impedance of the two media. The greater the difference, in the acoustic impedance, the larger difference. As I said, guys, two surfaces Z1, Z2. If Z2 is way greater than Z1, then the ultrasound won't even bother going to this medium. It's just going to reflect back. But if they're similar to each other, almost similar, then it'll pass through or reflect or absorb some and then reflect some. Understand? What is the basis of imaging ultrasound? A part of an ultrasound beam is reflected at the interfaces of different tissues with different acoustic impedances. So the boundaries of different tissues can be mapped using the intensity and delay of the echo compared to the impulse leaving the transducer. As I said, the boundaries of different tissues can be mapped, like I said over here, in an A mode image. The intensities of the rays coming back is mapped out in an A type image, and then we use a B type image to map the pixels, and then boom, we get a beautiful image. That's the ultrasound. So I hope this was helpful, and I'll see you guys probably in the next video. But guys, I'm trying my best to make these videos, but I want to study as well. So I hope you guys understand if I can't really make it, but I'm going to try my best. Okay, so I'll see you guys in the next video if I do. I love you guys. Hope you guys have a great SCT tomorrow.